Hey everyone, Ashton here, and welcome back to Precision Horology. Today we're going to go through something quite interesting. Here we have an Omega 501. This is a pretty vintage caliber now, the 501. Omega don't have a lot of parts available for it anymore due to the fact that it's so old. The 501 is actually based on the Omega 470 caliber. And again, the 470 parts are scarcely available for this movement. This particular watch is in pretty good condition. As we can see, the movement appears to be in quite good condition. Unfortunately, when it came in, the automatic block, the actual whole automatic block was missing, and it became a manual wind watch. So only a few of the automatic components are available from Omega, so we can't get the parts that are needed to bring it back to being an automatic watch. If the parts were there but worn, there's things we could do, but because we would have to source the whole block, the two bridges, the wheels, the screws, the bushings, and the actual oscillating weight, that's going to be pretty difficult to do. So the customer has opted to leave the watch as a manual wind watch. Now, there's a particular issue we need to address with this movement, and that has to do with the barrel arbor and the bushings. We can see that the barrel has still been left in place in this particular watch. Now, as we know, the mainspring is housed inside the barrel, and to turn the mainspring, the ratchet wheel, which sits on top of the barrel arbor, like so, is turned, and it turns the barrel arbor to wind up that spring. Now, the barrel arbor is made of steel, and the plate or the bearing that it's in is made of brass. So what happens is when there's not a jewel present, and we have a bushing or a hole in the plate made of brass, that hole tends to wear. It starts to wear oval as it's wound, and we see that we have movement there. Now, we need freedom, we need play. It's very important that we have up and down end shake like so that the wheel can move freely. And it's important that we do have side shake as well. But what happens when it gets worn and we have too much side shake, the barrel will tilt over. And what can happen when the barrel tilts over is it can actually foul the center wheel. So the barrel can tilt up, and we can actually hit and affect the center wheel. And then that will affect amplitude in the watch. It'll rub, it'll create metal dust, and it'll start to stop the movement. Now, this particular example in this watch, it's certainly not the most worn I've ever seen for a barrel arbor and a bushing, but we don't like to think 12 months or 2 years down the line, what's going to get us through the warranty period. Now, this watch would probably get us through the warranty period. I offer a 2-year warranty with all my work, so to be honest, that kind of wear, I'd probably be okay. And then the watch would be back in 2 years after the warranty was up, and I could service it again. But that isn't how I like to do things. I like to address this problem. I like to think 5, 6, 7 years down the line. So I don't want to see this watch come back. I want to address all the issues, correct all the problems now, so that I don't see this watch back again anytime soon. So what we'll do is we'll head over to the microscope and we'll have a bit of a closer look at this barrel arbor and the bushing. So we can clearly see the presence of gunk around the barrel arbor here, around the bushing. Now, when we grip the barrel arbor, we can see that we can feel that we have end shake, but we can see that we have too much side shake here. Again, like I said, it's not horrendous, but it's still something that we need to address. So let's go ahead and get this bridge off, and see what we're working with. So we have all our components separated now. We have our barrel removed. We have a lot of excess lubrication on the outside here, but that's not an issue. We have our bridge removed, and we can see our main plate here. So now we have to ascertain whether the issue is with the bottom plate or the issue is with the top bridge. Now we know that we saw wear in the top bridge, so we know that the top bridge is going to need to be addressed. But maybe we also have wear in the bottom. We didn't check that. So we're going to actually physically examine the holes now to see what we can find. So first we're going to use pegwood to clean out the holes to make sure all the dirt and debris is removed. And then we can look at the actual holes and inspect them, physically inspect them for the wear that we can see. So here we can see the worn brass ring and the way that it's cut away at one side, so there's definite wear. If we look at the side profile, we can see that the plating has worn away and we can see the brass come through. So now that we know what we're working with, we can get to measuring. So what we're going to do is we're going to change our barrel bushing, and our bushing looks pretty good in our main plate. So we're going to change our top barrel bushing, and then we're going to see, once it's all together, what our main plate looks like and how the whole thing assembles. And then we're going to decide from that point whether we need to do a bushing for the main plate or we're going to be okay. So I think we're going to be okay. Everything looks pretty good there. But that's our best way of checking. So we're going to use our vernier gauge to measure up. So what we need to measure is we need to measure the bearing surface of our barrel arbor. So we need to measure the surface that it acts against on the barrel arbor. We need to measure the height of where the bushing is going to sit in the plate. And then we need to see how much we need to bore out to get a bushing that is not too small, that fits in nicely. But remember, we obviously have clearances and things to work with because we can't drill out the plate because that's going to cause problems. So we're going to get to measuring and go from there. So here we have our measurements. Our bearing surface, or basically the hole inside the bridge here, is 1.6 millimeters in diameter. So when we make our new bushing, we need to have that hole 1.6 mil in diameter, or when we modify an existing bushing. Now, the thickness of our plate, our actual plate is 0.3 millimeters thick in this area, but our bushing, or our section that has the hole here, is 0.4 millimeters thick. So it's raised up slightly on the top, and it's also raised up on the bottom here. Now, this is probably to account for end shake and things like that when it's manufactured. And the diameter that we're going to cut is, well, the diameter across of this section is 2.45. So what we're going to do is we're going to fit a bushing in here, but we're going to make sure that we don't completely cut away this 4 mil section, this 0.4 mil thick section. Because if we leave a section of this 0.4 mil, it means that we can, it means that basically we can fit the bushing in with the largest section possible, so that when we press it in, we've got more meat that we can friction fit into than the 0.3. We've got the 0.4 to friction fit into. So let's head over to the lathe then, and we can start drilling out our hole. So at this point, we can head over to the lathe and get ready to start boring out our hole. Now, we attach our movement into the faceplate. The faceplate allows us to set up things off center. Once they're set up off center, we can drill out and bore out. Now we find rough center with a centering punch or a pump center. And then what we do is we find exact center with our centering microscope. So if we head on into our centering microscope, we can see that we have crosshairs, and those crosshairs help us find exactly the center of the piece. Now what we do here is we use the side of the hole so that we get a straight line on that side. Now we can't use the actual hole because remember the hole has worn slightly oval. So we need to use another reference point, and we can use the machine piece that is around the hole as our reference point. So we're going to use a wooden mallet to tap the work true so that we can get the watch, the hole centered up. So we take our wooden mallet, we rotate the work, and we tap it true like so. So I do apologize, it's very tough to center up. It's very tough to focus through the microscope here. But there we can see we've tapped it true and we're on center. So we haven't found the center of the work, we've found a reference point, and that reference point isn't wavering off our line. So now that we've found exact center of the piece, we can go ahead and start boring out the work. So we set up our workpiece like so, and then we start to bore by turning the compound slide here in and out and up and down so that we can bore out that hole nice and neatly. And we can see here this is the setup of our compound slide, which enables it to go in and then out this way as well, so it's set up on multiple axes. Now this is safer than drilling because this gives us a much neater hole. It's called single point cutting, and single point cutting is the most precise way of cutting. We don't have any movement or fluctuation like we would with a drill bit. Drill bits can be used, especially for a barrel, but in this scenario, we're going to be using a single point cutter. So now we have our hole bored out. We can see that we have our hole here that's been bored out nicely. We've kept our 0.4 mil ridge there. And what we'll do at this point is we're going to go and turn up our bushing over at the lathe. So we start with some stock brass that's been trued up on the end here. And we've flattened off that surface, we've faced it off nicely, and we have started our small pilot hole to find center for our drill bit. Now, if we don't kind of start the hole, we get a bit of an off-center wobble when it comes to the drill, when we drill it out. So we want to start that hole small. So now what we'll do is we'll turn the body of the brass, of the rod, up to size, so that it'll be the exterior of our bushing. So now we have our piece turned to size. It's the correct size now. It's a little oversized in the sense that we have to friction fit it, so we leave it a bit bigger than our hole. But yeah, we have it ready to go, and we can go to the next step, which is cutting the back off so that we can drill through our hole for the arbor. So we remember our hole has to be 0.4, so we use some marking die, also known as a Sharpie, and we can measure our 0.4 distance, mark a line, and then we know how thick our bushing needs to be. So we now have our bushing turned to size, and we've undercut the back. Now we undercut the back to less than 1.6, which is our inner hole, and then as we drill the hole, the bushing will come straight off the piece, and we don't have to part it off later. We can now go ahead and drill our workpiece. So here we can see that our bushing is complete. We can see that we have a new brass bushing installed, contrasting to the plate. And we can see that we've taken up all that side play, all that side shake that we had, all that slop that was there, and we've tightened that up nicely. So a successful operation now with that new bushing mounted in place. And in fact, we actually ended up changing or boring out and fitting a bushing in the main plate, I should say. After careful examination, it showed that it was more worn there than I would like to have seen. So we decided to go ahead and change that bushing out too. So if we look here, we can see we have a new brass bushing that's been installed in the main plate there. So now that we've corrected all those faults, we can get to cleaning and we can assemble and lubricate the watch. So thanks for watching, guys. I hope you enjoyed the video. If you did, please stay tuned for the next one. Subscribe to the channel so you can get updates. Like the video. Check out the website, precisionhorology.com, for any work that you might need doing. And you can check out my Instagram as well. So thanks again for watching, guys. Hope you enjoyed, and we'll see you next time.